Your speakers today will be myself, Barry Reeker, Commercial Manager for Food and Beverage, Kurt Rosentrader, Executive Director of Distiller Grains Technology Council, Professor at the Iowa State University, and Jose Molina, Business Developer and 25-year technical expert in anaerobic digestion. Our presentation will be recorded today. We expect to take up about an hour of your time and leave about 10 minutes at the end for questions. You may use the chat box in the GoToMeeting interface to type in your questions. We'll address them at the end.
Thank you very much. Good morning, everyone. For those of you that know about the Distillers Grains Technology Council and have met me before, it's great to have you here again today. For those of you who aren't familiar, hopefully by the end of the discussion, you'll become acquainted with some of the work that we've been working on and doing and trying to move our industry forward. So as what Mike said, I'm at Iowa State University, but I also am Executive Director for the Distillers Grains Technology Council, and I'll give you a little bit of information about that as we move forward. Next slide, please. So the context for the conversation we're having today was born out of a recent event that the Distillers Grains Technology Council held in Louisville, Kentucky back in October. And one of the things that we've been working on is trying to help improve the sustainability of the beverage industry, the biofuels industry, looking at multiple facets of the triple bottom line: sustainability in terms of environmental aspects, in terms of economic aspects, and in terms of social aspects. If you are fermenting products, whether it be cereal grains or molasses or sugarcane, you're trying to produce some kind of alcohol, you're going to have byproducts of some kind. And the ethanol industry has done a really good job over the years of taking what had been a byproduct material and actually adding a lot of value and improving the sustainability not only of the factory operations, but also of the local farming operations that utilize these feed products. And so when we think about this triple bottom line, we're really talking about not only improving our environmental footprint, but making more money for our company, making more economic generation in our communities, developing relationships with farmers in the community in terms of feed products that we are potentially putting into the agricultural marketplace. Next slide, please. So here's kind of what I wanted to talk about over the next couple of minutes, kind of talk a little bit about our motivations as a council, sort of the history of our council, how we've been working on these sustainability aspects for some time now, talk about some of the processes and co-products that we might be working with and dealing with at our production facilities, talk about economics, talk about dewatering, and maybe a few other issues as well. Next slide, please. So history and motivations is where we will start. The Distillers Grains Technology Council was actually formed in 1945 by a couple of companies you may have heard about before, Seagram's and Hiram Walker. And they formed this organization to try to improve the sustainability of the beverage alcohol industry back in the 1940s. Next slide. So really, the reason the council was formed was because the states of Kentucky and Tennessee had started implementing environmental regulations that restricted the disposal of stillage or spent grains from the fermenters into the local rivers and lakes. And so the idea was, well, what should we do? What could we do with all of these non-fermentable materials? And instead of dumping them into the rivers, animal feed products and use as an animal feed ingredients really were sort of the best option at the time. But even further back, even in the 1800s, the beverage industry was using wet spent grains and dry spent grains as animal feeds, and we were actually exporting dried spent grains to Europe for animal feeds. So next slide, please. When we think about fermentation and industrial fermentation, whether we're making alcohol for humans, alcohol for cars, or alcohols for other industrial uses, it's not just about the alcohol that we're making. We also have to consider all of the non-fermentable components. If we're talking about making any type of alcohol from a cereal grain, whether it be corn, wheat, barley, rye, triticale, or other cereal grains, there's going to be a lot of protein, fiber, fat, and minerals that we have to deal with in addition to water. So we'll have to think about the flip side of the coin. It's not just about the alcohol production. And I think this is especially true whether we're talking about small distilleries or large distilleries. You know, if you build a small distillery that is going to be in the city center, whatever city it is, you know, some of the things you're going to have to think about are not just the electricity and the logistics of getting the grain in and the alcohol out. What are you going to do with all the non-fermentable materials? And sometimes that is a constraining factor for facility construction. Next slide, please. And if we're talking about using non-fermentables as livestock feed, which many companies have very successfully done, the biofuels industry is really done a fantastic job of doing this, but this may not be the best fit for you. But a lot of companies do see this as the easiest way to not just get rid of or deplete the stillage from your facility, but also how can we reduce the cost of treatment and how can we make money? So it's a balancing act between those who are manufacturing alcohol, the livestock producers that you need to foster relationships with, and also the price and the availability. If you're giving away the stillage or the spent grains, you're really talking about lost profit. And then you can further compound that by the fees or the fines if you're sending the stillage down the drain for the city municipal system to treat. So next slide. When we are doing industrial fermentations and using our non-fermentable components as livestock feed materials, you know, it's easy to think about livestock as a black box, whether it's a fish, a cow, a pig, or a chicken, or a horse. You know, what do we control? What do we do at our alcohol production facility that's potentially going to impact what happens on the farm and what happens in that animal? Everything we do in our fermentation or post-fermentation is going to potentially impact how that animal digests that feed ingredient. And remember, we're working with proteins and fats and fibers and minerals. Next slide, please. It's been shown over the last couple of decades that on average throughout the US and in other countries, if we are doing industrial fermentations and using those non-fermentable components, either as a dry distiller's grains or a wet distiller's grains, on average, that DDG is going to replace between 1 and 1.2. So 1 ton of DDGS will replace 1 to 1.2 tons of corn and or corn soybean meal mixtures. So corn and soybean meal are the 2 biggest competitors on the national scale for distillers grains. So let's go to the next slide, please. So processes and products. So whether you're making beer or you're making spirits or you're making biofuels, the theoretical yield that we're going to get from alcohol fermentation of cereal grain, and this is true for cereal grain, it's not true if you're doing a grape fermentation or a sugarcane fermentation or molasses fermentation. But if you're doing a grain-based fermentation, the maximum theoretical yield, if you had 100% efficiency, is approximately a 50-50 split between alcohol and carbon dioxide if we're looking at the glucose utilization coming in, out of that fermenter. So remember, we're using cereal grain because it's starch bearing, but what we're really trying to access is the glucose. Now, in reality, we're going to have more than just alcohol and CO2 that are being made. And part of that is due to yeast cell mass that is going to be produced, and then secondary products, the fusel oils, the higher and the lower alcohols, not the ethanol that we're targeting. And sometimes those components are important, especially for flavor, and sometimes they're not. They're just essentially represent a yield loss. On average, it's been shown that for cereal grains, for every pound of cereal grain, whether it's corn, wheat, barley, rye, or whatever that goes into that fermenter, you're going to get about 1/3 of a pound of alcohol, 1/3 of a pound of CO2, and about 1/3 of a pound of non-fermentables, whether it's dry or wet form. And so that rule of thirds, that is what we typically see. Now, your facility may do a little better or a little bit worse depending on your production practices. And that rule of thirds then can be translated into, on average, a bushel of grain that goes into your facility will yield at most about 2.9 gallons of alcohol if you're doing traditional alcohol fermentations and you're not doing fiber fermentation or some of those evolving types of processes that are being implemented in the ethanol industry. About 2.9 gallons of alcohol and 17 to 18 pounds of CO2 and 17 to 18 pounds of non-fermentables. Next slide, please. So when we look at spirits manufacturing, whether you're looking at whiskey or vodka or other types of spirits, many of the factories are going to be similar in many respects to an ethanol plant, what we typically think of in terms of corn-based ethanol. Not just in the US, but in other countries as well. And the circle in this slide represents the co-product processing. And depending on what you do as a factory and your scale as a factory, you may have stillage that you're dumping down the drain, or maybe you're doing some type of a solid liquid separation and then giving your solids away to some local farmers or selling those solids. And then the liquid stream, typically most companies are going to be sending down the drain to the city if they do any solids liquid separation at all. Some companies, especially the larger distilleries, are going to be doing, they'll have an evaporator step where they will concentrate the thin stillage that comes from the centrifuge to produce a syrup, and then they can add that back to the wet cake to produce a distiller's dried grains with solubles, or maybe distillers wet grains with solubles. But there are other things that we can do. We see, especially in the larger factories where they have the wet and the dry products with or without solubles. They might have wet solubles sold separately or dried solubles sold separately. It really depends on scale. Next slide, please. So if you haven't seen distillers dried grains or distillers wet grains, these are typically what you're going to see. And then you also see that there are condensed solubles in the upper left hand of the slide. And the color of each of these products is going to be very, will resemble to a large degree the cereal grain that's coming into your facility. In this case, we see a golden yellow. This is a corn-based fermentation. If we have a rye or a wheat-based fermentation, we're typically going to see darker solubles, darker wet cake, and darker DDG. So color is, by and large, highly impacted by the type of cereal grain that you use in your facility. Next slide. When we look at composition, and we're going to talk about composition because historically we think about using non-fermentables from the beverage industry for livestock feed. What do livestock nutritionists worry about? They worry about lots of things. Protein and fat or lipids are part of the story, but nutritionists are increasingly looking at amino acids and fatty acids as well. So in terms of protein, for example, and all of these nutrient values are given on a dry basis. So crude protein, condensed solubles is about 20%, thin stillage is about 18%, and distillers wet grains without solubles is about 44% on average. You'll also see the fat or the lipid about halfway down the slide, about 17% fat in condensed solubles, about 9% in thin stillage, and about 5% in distillers wet grains without solubles. Next slide, please. If you dry your non-fermentables down into a DDG or a DDGS, in this case, we're talking about distillers dried grains with solubles added, protein is going to range from about 25 to about 34, 35 for most distillery operations. The ethanol plants are actually producing significantly higher protein, but they've implemented or are starting to implement some protein extraction technologies that we typically don't see in beverage distilleries at this point in time. The fat contents for distillers grains, generally we're going to see ranging from 7 to about 16%, depending again on the type of cereal grain that you're using for your fermentation. The ethanol plants are by and large removing oil and selling that oil to the biodiesel industry. We see some of the large distilleries starting to do that as well. Next slide, please. We talk about malt whiskey fermentation, a little bit different process. This really does not resemble an ethanol plant anymore. We see a couple of different types of co-product materials. We see a centrate, we see draft solids, we see potentially pot ale syrup that is added to the draft to produce distillers dark grains or distillers wet grains. We see spent lees that might be produced from secondary still. So the byproducts from this type of manufacturing are going to be a little bit different. And we'll go to the next slide. And just to kind of show you, here's an example of what pot ale syrup will look like. That's the syrup that is in some respects similar to condensed distiller solubles from a whiskey or a vodka plant. And then draft is very similar again to distillers wet grains that you would see at a whiskey or a vodka plant. Next slide. In terms of nutrient content, again, protein and lipids are two of the critical nutrients that we look at for livestock feed applications, but the nutritionists really are wanting to understand the full suite of nutrients, including amino acids and fatty acids. But in this case, if we look at crude protein, for example, pot ale syrup is about 37% crude protein, so it's going to be a little bit higher in protein than we would typically see from a distillery that a whiskey or a vodka distillery that's producing condensed solubles. Draft is about 20% protein, and these again are on dry basis. And then distillers dark grains without solubles is about 28%. So in that case, that is quite similar to a distiller's dried grains from a whiskey or a vodka plant. If we look at fat, the pot ale syrup is going to be really low in fat content, almost 0%. Or if there's any fat that has been extracted, it's going to be quite low. Draft is going to be about 8%, and distillers dark grains are about 8%. So why are these nutrient values some similar and some different? I think the thing we have to think about is that, you know, we're talking about a grain out versus a grain in style of fermentation, and the way that we utilize the carbohydrates in the grain out fermentation, we're basically trying to extract the soluble sugars and make those solubilize so that we can pull those into fermentation. So really what we have left in the feed products are much more of the nutrients than we would typically see compared to a grain in fermentation. Right, next slide, please. Beer manufacturing also has non-fermentable materials, and again, when we talk about styles of fermentation, much of the beer manufacturing we see a grain out style of fermentation where we use hot liquor and we use the mash tun to try to extract the solubilized or solubilizable sugars. And in this case, the spent grain or the brewer's grain in many respects is going to be quite similar to what we would see from a malt whiskey manufacturing point of view. And we'll go to the next slide and take a look, and you'll see the spent grains, either dry or wet, in many respects is similar to what we would see as draft from a grain out style fermentation, a malt whiskey fermentation. Next slide. Nutrient content wise, protein content for brewer's grains is about 26%. Lipid or the ether extract is about 7%. So just like the draft that we saw or the distiller's dark grains that we saw from a malt whiskey fermentation system. So there's the biggest difference really is going to be in the mash bill that we're using for that fermentation. And depending on what state or what country you're in, what grains you can use. And we do see the dynamics of the beverage industry, whether it's whiskey or a vodka or beer. We do see lots of novel products hitting the marketplace over the last couple of years. We're not just talking about malted barley. We're also talking about a variety of different kinds of cereal grains being used for these industrial fermentations. And so we see the nutrient contents varying when we look at these co-product feed materials. Next slide, please. Now, I do want to mention, if you're going to be using your co-product feeds or your byproduct feed materials in the livestock industry, we as an organization, the DGTC, have developed over the last couple of years some guidance tools that you might be interested in using, talking about, what are the different kinds of feed materials that we see coming from these industrial style of fermentation. And specifically, we're looking at from distilleries and from biorefineries. What we used to call ethanol plants, we're starting to call biorefineries, because we see these companies starting to extract proteins and extract lipids and do some fiber fermentation. And so we really see biorefineries evolving in terms of the feed products that they're manufacturing, and they're targeting specific species, especially with high protein or high fiber style of feeds. But if you're not moving in that direction and you're building a distillery or a brewery, what if we're going to be selling these into the livestock feed marketplace? What are we making? And so we've got some guidance documents that will hopefully be helpful for you. Next slide, please. So let's talk about some economics. What I mentioned, corn and soybean meal being the biggest competitors for our feed materials that we're going to be producing, whether it's brewers grains or distillers grains or draft, whether it's beverage or biofuel. We're competing with corn and soybean meal in the marketplace. And so it's important to understand the marketplace evolves quickly, and sometimes this is due to situations like COVID. Sometimes it's due to tariffs and trade wars with other countries like China, for example. Sometimes the feed values are dictated by supply and demand in the US itself. So just looking at the price of DDGS, distillers dried grains with solubles, this is for both beverage as well as biofuels. What we see is quite a variety, and we're looking from August of 2020 to August of 2021. We see this variety of weekly prices from about $150 a ton to over $300 a ton, and we see a lot of fluctuations. And for the reasons that I mentioned before, it's not just about what happens in the US, it's also about what is happening outside of the US that's leading to all of these fluctuations. So if you're going to be selling your feed material into the livestock industry, it's important to understand what is the value of this material, what's it worth to me as a company. And if you're giving it away, you're really not capturing that value. Next slide, please. It's also important to understand that what do most farmers replace in their diets, whether it's beef, dairy, swine, or poultry? They're typically replacing corn or corn and soybean meal. And so if you are selling your product for more than 100% the value of the corn that's coming into your plant, then you're making some money off of that grain. If you're selling your co-product feeds for less than 100% the value of the cereal grain that you're bringing in, you're actually losing money on that bushel of grain. So that's something else to keep in mind. If you're selling your co-product for less than 100% the value of grain, then the livestock producers are getting a really good deal. If you're selling it for more than 100%, you're actually making money off the grain that you've brought into your plant. Next slide, please. So it's also important to understand, if you are a new distillery and you're trying to sell your co-products as livestock feed, you will be competing against the distillers grains that is coming from other distilleries, but also ethanol plants. And there are in the last couple of years about 35 to 40 million metric tons that are being produced every year. And about 70% of that stays in the US for beef, dairy, swine, and poultry, but about 35% is exported overseas. So most of the domestic use of distillers grains and brewers grains goes to beef and dairy, but there is a growing percentage that's also going into the swine and the poultry industry. And I think these are going to shift a little bit as we move forward over the next 10 years, as we see the ethanol plants start to evolve in terms of their protein products and their fiber products and their fat products. Next slide, please. So if you want to deal with your stillage coming out of your fermenters, how are you going to do that? Are you going to send it down the drain, or are you going to try to capture the value that's there and not lose that opportunity cost? So if some distilleries just provide their slop to local farmers and either they give it away or they sell it for 50 cents a ton or 10 cents a ton, it's expensive to ship water, whether you're shipping it or the farmer is shipping it. So and it's expensive to send your stillage down the drain and have the local municipality do the water treatment. So maybe an option that some companies are thinking about is separating solids from liquids, and that's going to reduce the cost for transport as well as potential water treatment. Next slide. So every city is going to be different. Every municipality is going to be different in terms of how to calculate what those fees or surcharges are going to be. You'll see that some cities, most cities use BOD as part of their calculation, but most cities don't use COD. Some do, but most don't. And it really depends where you're located to really understand what is that cost going to be to me as an organization, as a company, if I send this down the drain and have the city deal with this. Next slide, please. So there are lots of different separators that are available. Some are quite expensive and some are low cost. This is an example of a small centrifugal style of separator that separates liquids from solids. Next slide. How much do you need in order to break even? That's what I get asked quite a lot. If we're going to try to produce a product that we're going to ship to local farmers that's about 50% water, 50% solids, which is typical for a distiller's wet grain. If you talk about a really small scale centrifugal separator, it's about $35,000. If you're thinking about a large scale separator, that's going to be more like $100,000. So really, how many tons do you have to produce in order to break even? Sales price for distillers wet grain generally bounces around between $50 and $100 per metric ton. So somewhere between 350 and 700 tons you're going to have to produce. So depending on the scale of your factory, you can determine, how long will it take me to produce that. We'll go to the next slide. And just to do a quick little calculation to show you all, if you are producing between 0 and 40,000 gallons of stillage a week or spent mash a week, how long will it take you to achieve 700 tons? The bigger you are, the shorter it will be. So break even will happen. If the larger you are, you can approach less than 20 weeks in order to break even. So these seem to be really a good avenue if you're trying to sell a distiller's wet grain product into the market. You're still going to have to deal with the centrate or the thin stillage, which is primarily water and then the dissolved solids. And most companies that install these separators will sell their separated solids as distillers wet grains for livestock feed, and then they'll send the centrate down the drain to the city. And what we have seen is more than a 50% cost reduction for disposing of the stillage by using that approach. Next slide, please. Some companies do landfilling of their stillage, which again, it's expensive to ship water, but also tipping fees nationally are on the increase. So if we kind of take a look at what some of the trends are, the bigger you are, the more expensive it's going to be. And as we proceed in time, the more expensive it's going to be to landfill that stillage. So it seems to make sense to try to add value and not just landfill and not just send it down the drain to the city. Next slide, please. Well, next slide as well. A couple of other issues I wanted to talk about. Fermentation, beverage and biofuel fermentation use Saccharomyces cerevisiae, the standard brewer's yeast, and just in the last couple of years, we have seen livestock nutritionists really start to understand there is value in the yeast as part of the livestock feed ingredient components. So if we're sending this down the drain, we're really losing this value. Yeast acts as a prebiotic and a probiotic, and we're just now starting to understand that there's a lot of value in taking this yeast and sending it to livestock as a feed ingredient. Next slide, please. If you do that, again, earlier in the presentation, I mentioned definitions. So the DGTC has developed a set of types of co-product feeds, and that is all revolving around AFCO, or the Association of American Feed Control Officials. You cannot legally sell a feed ingredient in the US without a legal definition as published in the AFCO official publication. And luckily for almost all of the breweries and distilleries in the market right now, there are definitions that your product can fit under. So this makes your life easier. Next slide, please. If you do sell your stillage or spent grains as an animal feed ingredient, you know, it's great that we've got AFCO definitions ready for you all to use, but you will have to comply with the FDA's Food Safety Modernization Act. So you are producing a livestock food, and so you'll have to follow the federal regulations in terms of facility sanitation and cleanliness, and then hazard control, so that we're not poisoning animals or potentially causing problems with those animals. Next slide, please. So this sort of reaches the end of where I wanted to talk about. This is my contact information. I know you'll have that again later, and we'll jump to the next slide, because I think where I want to leave you all today. Oh, I guess where I wanted to leave you all was, there's no one size fits all. If you're a small distillery or a large distillery, if you are in a rural area, or if you're downtown, whether it's New York City, Chicago, or other large city, there's no one size fits all solution. And livestock feed works for a lot of companies, but it doesn't work for every company. And so I kind of want to transition over to the folks and team at Evoqua to talk about technology that can help in our portfolio of, you know, answering the question, what do we do with our stillage and our spent grains?
Thanks, Kurt. Well done. I'm going to just very quickly go through some capabilities, and then I'll hand it over to Jose to go through more of a technical look at how anaerobic digestion can perhaps work in conjunction or perhaps in place of some of the processes that Kurt just described. So if those of you who aren't familiar with Evoqua, we're a solution provider to the food and beverage industry, among others, specifically pertaining to distillery. We focus on anaerobic digestion, as mentioned, handling the digestate coming off the anaerobic process. Nutrient management can either be removal or recovery. We do biogas upgrading and facilitate utilization. We look at in-plant water process, water stewardship as well, including wastewater reuse. We're highly experienced in the business, been doing anaerobic digestion systems as Evoqua for over 100 years. We have 100 full-scale biological reference installs, 400 on industrial wastewaters, 40 anaerobic digestion reference installs on stillage, 5 anaerobic processes and 4 aerobic processes to pull from, and the full complement of physical, chemical, filtration, and membrane separation technologies that you need to facilitate either direct discharge or wastewater reuse. Here's a quick look at the global reference installation map. You will see that red, green, purple, and blue are anaerobic installations. Orange and yellow are aerobic polishing installations. And the little green dots are dissolved air flotation. Here's another look at the distillery specific reference installations and process used. I would be remiss if I didn't mention commitment to sustainability. Evoqua is aligned with the United Nations Sustainable Development Goals. We, of course, primarily contribute to clean water and sanitization, although we also play a role in affordable and clean energy, responsible consumption and production. We measure and manage our sustainability commitments through both our handprint, which is how we help you guys, our customers, accomplish your own goals, and our footprint, which is how sustainable we are in our own operations. Evoqua is a service organization. As you contemplate the many permutations and combinations of dry distillers grains and/or anaerobic digestion, it is often helpful to know that service and support is available. Evoqua is the largest service network in North America. We service, support, operate, and maintain everything that we sell and many things we don't. As with any high-strength organic feedstock or waste material, however you want to view it, it's often helpful to have analytic and lab and piloting and bench scale capabilities available to you. We do, of course, have those. Stillage is a complex material, and it is often helpful to start at the lab to validate assumptions, methane potential, toxicity testing, and so on as you develop your project. I'd also like to mention that we've recently launched a Sustainability and Innovation Hub in Pittsburgh just earlier this year. This facility will be used for stillage digestion research and development, among other things. This is a state-of-the-art facility intended to be not only a technical hub, but a commercial hub where we can co-develop projects with interested parties. Having a quick look at the big picture, and I kind of look at this slide as why are we here today, or how did we get here? We've got quite a few things kind of lining up and working for us, and then we've got a few things working against us too. Nothing is, of course, easy. As you all know, demand is high. Most distillers I'm talking to are either currently or planning to increase their production. The economics of DDG, as Kurt mentioned, aren't simple. There's a lot of factors involved there as well. And there's perhaps a thought that it is more inclined or more suitable for the larger processors to absorb that type of infrastructure and investment to play in that market. When we look at the economy overall, especially the fuel economy, we of course seeing strong support and incentives around renewable fuels. So that is increasing the value of biogas and decreasing the cost of converting stillage to biogas. That, of course, aligns well with corporate sustainability goals as we all endeavor to reduce our greenhouse gas emissions and carbon footprint. And if you think of DDG and the energy inputs required, it's inherently an energy intensive process, which can also further enhance the attractiveness of a low operating cost alternative or a net energy positive alternative of anaerobic digestion. Of course, as Kurt mentioned, brewers grains are similar to DDG, and the distillery industry can simply look at the brewery industry as an adjacent market that successfully adopted anaerobic digestion as a primary treatment process. What's working against us? Costs money to get into the wastewater business as well. It depends on, really, as Jose is going to get into, it depends on what type of discharge permits you have, how many unit processes you're going to need to invest in order to create an effluent that's compliant. I'd also argue that there's declining organic wastewater expertise out within the industry. Increasingly, folks have to go outside of the organization to a consultant or a vendor like Evoqua to even get orientated or come to a webinar like this to get educated on what the options are. As I mentioned, it is in a challenging wastewater that we often want to validate in the lab before going to full scale. And quite frankly, there have been failed attempts at stillage digestion in the past which we would characterize as a misapplication of technology. As Kurt mentioned, there is no one-size-fits-all solutions, but there are capabilities and teams in place to help you understand what your options are. Jose, over to you.
Thank you, Barry. So again, to put it into context, what we're discussing here, this is just an introduction. We're trying to discuss some of the topics around the idea of, with this, the co-product from alcohol production, instead of looking at getting a value out of it by drying it and selling it as animal feed. An option that might be put in front of you from Evoqua would be to take that same material and digest it anaerobically instead, turn that food value still present in the stillage and turn that into a form of green energy rather than drying it up and selling it as animal feed. So we'll talk very quickly about some of the issues around anaerobic digestion. And as you take the energy out in the form of biogas, there might still be other things that you need to deal with, such as nutrient removal, nitrogen and phosphorus. What do you do with that biogas that you're generating? How do you get the most value out of the biogas you're generating? There's also some waste products out of anaerobic digestion that we will discuss on what we do with those waste sludges, and can we really get a value out of it in the form of fertilizer as well. Next, Barry, thank you. So stillage, as Kurt was describing, you have, after you've taken the glucose in the sugary material in that feedstock, as you've converted that into alcohol, there's yeast that does that in the absence of oxygen. Yeast takes the glucose into alcohol. There is still all that material, that organic material that is food, but that does not go through that biochemical pathway towards alcohol. There's still a protein and the fat, oil, and grease that remain in the stillage. Very strong material. You're making that soup, that broth that you made in order to ferment the sugars. What's left over after distillation has a lot of organic content to it, a lot of nitrogen, a lot of phosphorus. Depending on what you're using for your feedstock, whether it's corn, rye, or sugarcane molasses, that will also affect the amount of non-degradable or slowly degradable material, the amount of ash still present in that waste material. We will take that into consideration as we look at the overall picture of your stillage and look at the right way to get that value out of it, other than just disposing it in a landfill, like Kurt was saying. So here, what we're doing is in a way, it's the same concept. We're, instead of feeding cattle or livestock, we're feeding anaerobic microorganisms that will turn the protein left over in the stillage into that energy. Okay, so just very basic fundamentals on anaerobic treatment. And you can think of an anaerobic reactor in a way similar to making alcohol, where instead of yeast turning the glucose into ethanol, we have is a whole consortium of anaerobic bacteria that anaerobic microorganisms that again, in the absence of oxygen, will transform the organics into biogas, into methane mostly, and also some CO2. And there will be some remaining organic material that maybe some of those organics that are not fully degradable anaerobically might still be left over in the digested in the liquid form. And also some of the energy in the stillage is converted into new biomass. So you will have an excess, maybe out of 100 pounds of COD that come in, you will have 5 pounds of digested new bacteria that you will remove from the system as sludge. A slightly different process takes place under aerobic conditions. So if you look at the graph on the right, when you have organic matter, 100 pounds of COD, if you want to remove that aerobically, what you have is an energy input. You have to add oxygen to those microorganisms so they can do their work, convert the organic matter into CO2, a lot of heat, and a lot more biomass. So aerobic treatment will create a lot more waste material in terms of sludge than anaerobic treatment. A lot of the time, depending on where we need to take that digested stillage, we may need to use a combination of anaerobic treatment, get the energy out, but then follow it with aerobic treatment in order to bring the wastewater maybe to compliance for discharge, also control the amount of nitrogen and phosphorus that goes out in that final effluent. Whatever other objective we need to meet locally will affect the level of treatment you will have downstream from an anaerobic digester. But again, the great value in this process is that green arrow that you see on the left. All of that organic is going into a green form of energy that you can recover and utilize. In a lot of cases for distilleries, you can approach or exceed energy self-sufficiency. So rather than buying natural gas or other fuel into the plant for running your distillation process, you will be able to close or come close to closing that loop and using your own energy in terms of fuel demand for your plant. Next, Barry.
Jose, in the interest of time, I'll ask that you go through comparing and contrasting different processes, digester types, and so on fairly quickly, and
Sure.
make sure we can get to case studies and then have some questions.
Yep. Okay, so again, the idea is to apply the right technology to every particular situation. We'll look at the technical side, we'll look at the economics, and the solution will be the right combination of technical and economic factors into it. What you do after anaerobic digestion will affect whether you need to do some post-treatment on that digested effluent. As we said earlier, one advantage of talking to Evoqua is the fact that we have at our disposal a whole series of anaerobic digesters. So it will be a case of us using the most appropriate technology for the particular needs of each plant, and we'll look at the local conditions, treatment objectives, economics, of course. This is just to give you an idea of what those reactors may look like. I will concentrate on the reactor on the top left, so that's the low rate ADI PVF reactor. The reactor on the bottom left would be the anaerobic MBR system. And what we are using also for stillage digestion will be a form of a CSTR, so on the bottom right. So I'll go quickly through those as examples of what you can do with stillage. The PVF reactor has been used at over 40, I would say, distillery plants around the world. A lot of them are sugarcane molasses-based distilleries, but also this system has been used at distilleries in North America for the treatment of ethanol or alcohol being made from the more traditional to our audience, corn or similar cereal grains. The PVF reactor is characterized by the long retention time, so it's a large reactor for the amount of load that you're treating. But again, that large volume gives you the stability required, the time required for digesting not just the complex proteins that are in the stillage, but also the organic, volatile, digestible solids that are still in there as well. So this type of reactor is very good because it can do the stillage, it can digest the stillage straight up without any pre-treatment, without any removal of the solids or the fat, oil, and grease. The same applies to a CSTR type of approach. As I was saying, that would be the medium rate reactor. With the main difference between the CSTR and the PVF reactor is the fact that after you come out of the anaerobic digester, you will need a unit operation to separate the solids from the treated stillage. So in this case, we will look at each specific situation to decide on the type of separation, whether it's flotation, whether it's membranes, there's a physical barrier to remove those solids, or perhaps a centrifuge or some other form of physical separation of the biomass, keep the biomass in the anaerobic environment, and then discharge a liquid stream with a very low concentration of suspended solids. Again, this is still ideal for treating stillage straight up without any pre-treatment. Finally, a more recent development in anaerobic digester technology is the coupling of the CSTR, so the continuously stirred tank reactor that you see on the left, and a membrane separation unit process. That's what you see on the right, where we were taking ultrafiltration and microfiltration membranes to keep the biomass inside of the system, and then discharging in just a clear effluent with no suspended solids. Again, very well suited to very high COD, very high suspended solids concentrations that you'll see in stillage. So as I said before, the anaerobic digester will take the proteins and organics and convert those into methane. It will not do much to nitrogen and phosphorus. So the high concentrations of nitrogen and phosphorus that you'll see in stillage, you will still need to deal with or pay your downstream POTW, your sewer, your municipal treatment plant. You may have to pay for them to treat it for you. In some cases, that is the case. In other cases, where maybe the downstream process does not allow you to discharge high nitrogen and high phosphorus, we will need to treat that nitrogen and phosphorus prior to discharge. You want to avoid situations like you see in the picture where you have eutrophication. You have nitrogen and phosphorus serving as a growing material for algae in your riverways and lakes. So here are a couple of options that we might apply for post-treatment, right? So this is treatment after anaerobic digestion, after taking the out. You will still need to do some aerobic treatment in order to bring your water to compliance prior to discharge. So the aerobic system is able to reduce COD, but also nitrogen and phosphorus to depending on what those limits are that you're trying to meet. So as we get into analyzing stillage, again, we talked about how we're making biogas out of it. There's a green energy in there. How you use the biogas is also something that we can help your company decide. What's the best way to use the biogas? Is it best or easiest to burn it in a process boiler? So in that case, you don't need to clean it so much. If you're going into a more advanced way of utilizing the biogas, like electricity generation or putting that gas back into a natural gas pipeline, then you will have more sophisticated and more complex treatment processes to clean the biogas. Again, we will work with you in looking for those better ways or the most appropriate way of handling that biogas. So what do we call success? Success for us would be our ability to match the needs of your particular situation, your local variables, your local objectives, and having that set of solutions that best match that set of variables in achieving your sustainability goals, whether it's converting that waste to energy, becoming energy and water self-sufficient, being able to reuse water. Again, those are all laudable sustainability goals, but economics comes into it as well. So there are cases where doing that anaerobic digestion, converting the stillage into biogas, will make the most sense overall for your particular situation. Again, we're talking about going down quite different approaches to handling the stillage. You can use energy and evaporate it and use it as DDGS and animal feed, or we can look at actually taking the energy out of it in the form of biogas and by using an anaerobic reactor for it. I will go very quickly here. That's the example I mentioned before, where you're taking a stillage, putting it into an anaerobic reactor, getting the biogas value out of it, and then having a aerobic treatment system downstream. So that's the right side of the graph, where we use aerobic bacteria to reduce the nutrients, nitrogen and phosphorus, but not necessarily recover them. So this is a typical train for when you have relatively medium-sized nutrient loads that you have to treat rather than recover. The next approach was another example recently where we were looking at a stillage with a very high concentration of phosphorus and nitrogen. And with the flows that we were trying to treat, it makes sense to here. On this chart, you see the anaerobic reactor. You're taking all of that sugar, sorry, all of that protein and fat, oil, and grease into biogas. And then you follow it with the process on the left here, where we have access to a technology that can do nitrogen, phosphorus. We add some magnesium to it, and we create a pelletized sellable product. Again, there's chemical addition, there is energy input, but you come out of this with a fertilizer product that you can sell to the market. You do this, you recover all of the phosphorus, you recover a lot of the nitrogen. You will still have a liquid effluent that needs some post-treatment. In this case, we go through a biological aerobic system that will do BOD, COD polishing, but also quite more advanced nitrogen control so that you can actually go out to final effluent with relatively low nitrogen, low phosphorus, and low BOD going out to effluent. So as I said earlier, we've been doing this kind of project for a long time. What we did see in our experience in foreign countries where maybe it's warm, so the digested stillage can be stored and land applied, so you're getting the water and the nutrient back into the land directly, rather than drying it and selling it as fertilizer. In cases like Thailand, you can do that. You can get the energy out, you can become energy self-sufficient, but there would be no treatment downstream because that water can be used for irrigation. But this is a great example of a plant that became self-sufficient. This is a system that, it's a fairly large distillery, so 160,000 gallons per day of stillage. That would probably be from maybe about 200,000 pounds of COD per day. So great energy value, and the company can get that energy out of the stillage and not have to use any external fuel sources for running that plant. So again, this is a plant that became self-sufficient in terms of energy as they digested their stillage.
Thanks, Jose. And pardon the pun, folks, but that's a lot to digest between everything Kurt went through and everything Jose has gone through. We didn't set out to solve all the problems today, and as we mentioned, there isn't a golden arrow or a one-size-fits-all solution here. There are actually an increasing amount of options for the modern distiller to consider as they seek to optimize the value of their residuals. So I would suggest in conclusion that the small to medium-sized processors that may be challenged by DDG economics consider anaerobic digestion either instead of or perhaps alongside of a DDG process. I would say the larger distillers should consider the economics and just do due diligence to make sure that, as I mentioned, they're recovering maximum value. I will remind you that the discharge limits play a large role in both the technology selection and, as a result, the cost of the project, which can make or break economics in some cases. The value of the biogas, which is really what we're trying to target here, varies considerably based on the method of utilization. I would finally suggest that the macro indicators that we're seeing suggest that this isn't the last we'll talk about stillage as a waste to energy feedstock. So with that, we'll thank you for coming. I realize we've ran late on time. We'll stay on for another 10 minutes and take questions, but understand certainly if you have to go. Any questions in the chat, Mike?
Yep, there's one. And the question is probably to Kurt. Who would you typically see pot ale syrup sold to?
Yeah, that's a great question. Thank you for that question. Similar to what you would see condensed distiller solubles from some of the distilleries and the ethanol plants. Typically, they are sold sort of as a top dressing for cattle feed, for beef and dairy. most of the ethanol plants have moved away from selling condensed solubles separately, and just incorporate that into the DDGS. But a few of the smaller ethanol plants still do that, and then some of the distilleries do that as well. So generally, it's the medium to larger scale distilleries. But the pot ale syrup and the condensed distiller solubles, oftentimes we see that sold as a top dressing for silage, for example, for hay, and then for other concentrates as well.
That was the only question in the chat box, but I think you guys came with a couple that people had asked you previously. You can address those if you wish.
Yeah, maybe I can add one that is more of a comment than a question, because I'll answer my own question, but I'll ask Kurt to also comment on it. So really, there is no line, is there, between taking the stillage to a DDGS market or taking it to a digestion system? It would be a moving line depending on everything: economics, location, size of the distillery. Would you have a hard line yourself from where you sit, Kirk?
No, I would say the same. I would say the same. And I think especially this year, the conversation has really gone down the path of sustainability and reducing carbon footprint and water footprint. And I see a lot of companies who are moving forward with trying to implement green energy and water savings technologies. And this seems to be one way to really kill multiple birds with one stone.
Okay, thank you, Kurt. Thank you, Jose. It's good that we can come together and present perhaps competing or perhaps complementary solutions to the distillers. If anybody has any questions, you can reach us directly with the contact information here. Otherwise, we thank you for your time. Look forward to seeing you next time.